Hey there, so today we are going to be starting solving exponential equations, and we're going to be looking at various strategies that we can use to solve these types of equations. So the first thing is equivalence. So for this question, it says, one student says you can solve the equation below, so that's this one right here. Whoops. By rewriting it using a base 4. Another student says you can solve it rewriting it using a base 2. So let's look at this and see who may or may not be right. And so here we got a to the 3 x minus 2 equals 4 to the 2x plus 2. Now I know that 8 and 4 can be expressed as 2 for sure. I know that 8 is 2 cubed. And I know that 4 is 2 squared. So this means that I can definitely rewrite both of these as base 2, because now I'm just going to go ahead and use my power of a power rule of exponents to simplify this so I have only one base with one exponent and solve the exponents. Well, that works. Well, what about for the base 4? Let's see if that works as well. So looking at 8 to the 3x minus 2, and then rewriting or writing this one for 2x plus 2. This one already has 4 on it, so we really don't have to deal with that side, but we do have to deal with this side. And this may not be as obvious, so let's see what we got here. Well, I can rewrite this as 8 3x, and I can write this as 8 and negative 2. So we can do that, which means this side here I can rewrite again. That's 8 cubed, and then I have this x on the outside here. And this one is 8 to the negative 2. Well, that's 8 squared, and that's to the negative 1. I can do that. Well, 8 cubed is 8 times 8 is 64, which is 64 times 8. And if I put that in my calculator, because I can't do things like that in my head and I don't know those cubes right off, I'm going to quit out of here, clear that up, and go 8 to the 3 equals 512. Well, that's one way I can do that. Now I'm thinking, that's a big number. I don't want to do that. So what I'm going to do, I'm going to look at my 64. Well, 64, I have a feeling that's 4 to the 3. Sure enough, that's 4 cubed. But I notice I'm still left with this 8 here. So let's go 4 cubed times, well, this is 2 times 4. Okay, we're looking a little better. This up here, 8 squared, that's 64, and we still have that to the negative 1, but 64 is 4 cubed as well, like this. And once I get to this, I notice I'm kind of done. Oops, I forgot my x's right here. This is 4 cubed, this is 4, this is 4 cubed, so these are all to the base of 4. The only one here that I have left is this 2, and I can't do anything with that. This one does not have a partner to pair up with to make, if there was another 2 hanging around, that might work, but we don't have that in this case. The only other thing we could explore is this side over here, where I would say this is 4 2x and 4 squared. Again, I have nothing here that could be broken down to pair with this 2. So we're done here. And that tells us that this student needs to rethink their plan. So going back to the first one here, we're going to go ahead and solve this algebraically, and we're going to use the power of a power, meaning this is going to be 2 to the 9x, and 3 times negative 2 is 6. And then here it's 2 to the 2 times 2x is 4x plus 4. And now we can equate the exponents. We're going to add 6 to both sides, and we're going to subtract 4x from both sides. So this gives me 5x on this side, and that gives me 10 on this side, which means my x equals 2. This time, let's graph this and verify the answer. So in my graph, I'm going to start by saying a to the 3x minus 2, 8 to the close the brackets, or open the brackets, 3x minus 2, and then in the next line, it's going to be 4 to the 2x plus 2. And let's hit the graph on that. Let's change my window settings to standard. Okay, there's one. Oh, and the other one. So this thing, looking at this, second calc, 5 for intercept. Is that the first one? Yes. Is this the second one? Yes. Do you want me to guess? Yes. But when x equals 2, we have this y equals 4.96. So yes, there is an intersection of these graphs and occurs at x equals 2. So for this question, it says, student said that he cannot use a common base to solve the equation 7 times 3 to the x equals 567. What strategy could he use to simplify the right-hand side of the equation so that he could use a common base to solve the equation? Well, the first thing I would do is I would go ahead and I would divide both sides by 7. So that means I'm going to go 567 divided by 7, and that gives me 81. So right off the bat, I now have something that I can work with. So this is going to be 3x now equals 81. And we know 81 is 3 to the 4th, which equals x, and which means x must equal 4. And we're done. Easy peasy. So do we want to check this? Well, we can check it by substituting it back into this equation. And we are going to go ahead and go 7 times 3 to the 4. Well, 3 to the 4, that equals 3 times 3 is 9 times 81. And look, we're back where we started. So we know we've done it right. Well, another way that we can solve exponential equations is to use the strategy where we convert the exponential form into a logarithmic form. So for instance, we can convert AB equals C into log A C equals B. So the base becomes the base of the log, C becomes the argument, and the exponent becomes what the log is equal to on this side. So let's look at an example of this. In this one here, it says a student knows that the exponential equation 5x equals 625 can be written as a logarithmic function as shown below. So see what they did. They took log of 5 of 625 equals x. How can she use this equation to solve for x? Well, now that she has this, she can do a couple things. She can go ahead and write this as log 625 divided by log 5. That's an option for her. She can see if 625 and is a exponent of 5. For instance, 5, I believe 5 to the power of 4 is 625. That's an option right there. So she could have done this a couple of ways, but here it's saying the student also tried applying the logarithm to both sides of the equation as shown below, and is asking us to annotate the solution. So what did she do? Well, she started with this original expression, 5x equals 625, and she went log of 5x equals log of 625. She brought the x down to the front, and now she got x equals log 625 divided by log 5, which equals 4. She put that in the calculator. And this kind of goes back to what I was saying earlier. One of the strategies would be to use the log 5, and that's where log A of B can be rewritten as log B log A. Remember, we can always do that if we want to convert it to some different base right here. And this basically shows that what she did is using that strategy, just in a different way. So the students solved the equation 3x plus 2 equals 15 in 3 different ways as shown below. So let's examine these. The first one, he took this expression as a exponent and converted it to a log. So he had logged 315 equals x plus 2. And he subtracted 2 from this side. So now he has this value right here. This one here, he brought the x plus 2 down to the front and then divided the right side by log 3 and then subtracted the 2 from both sides to get this. The second, or the last way he did is he graphed both sides of the equation. So y equals 3x plus 2 for the y1, y equals 15 for the y2, and found the intersection with a point of x equals 0.465. The next part of the question is, which of these solutions are exact? Well, these here are exact solutions in the blue and the red. They're exactly the value that we would have to put into our calculator, but remember the calculator is only going to spit back a rounded value because this definitely isn't a whole number or an integer value. So here we get x equals 0.465. So this one here would be the approximate. And you want to keep that in mind and look, are they asking for an approximate or are they saying round to the 10th decimal place or the 100th decimal place? So this question says solve the exponential equation 2x equals 16, and we're going to use that to help us estimate the solution 2x equals 15. So for this one here, we have 2x equals 16. Well, I know 16 can be written as 2 to the 4th. That means x must equal 4, and we're done. So how can this help us to estimate the solution of this one? Well, what I would do in this case, I would go ahead and solve 2x equals 2 cubed, where 2 cubed is 8. So this means that x equals 3. Now putting this on a number line, we know 8 gave us an x value of 3, and that 16 gave us an x value of 4. Well, 15 is much closer to 16 than 15. It's approximately right there because this can be split up into 8 pieces. We can say that the value for 2x equals 15 is approximately 3 7/8. We can do it that way. And if we wanted to write this as a decimal, I'll just go ahead, throw it in the calculator. And remember, it's an estimate. So 7 divided by 8, that's 0.875. So we can say this is 3.875. And that would be a way of estimating solutions. Okay, so we're going to continue on with solving exponential equations, and we're going to start with this example. So for this question, it says we have cobalt-60 as a radioactive material used in some medical tests. The half-life of this substance is 5.3 years, and that means that after 5.3 years, half of the original amount of the substance will be there. The percent of radioactive substance remaining, P of T, after T years is given by this equation. And if you've done some chemistry or some physics, you may have come across a half-life equation before. Now it's asking us to explain the meaning of each number in the equation. Well, the first thing here is that 100. So this is 100%. And that makes sense if the time equals 0, because if the time equals 0, because that's the t right there, that equals 0, 1/2 to the 0 is 1, and we are left with 100%. Because this is a half-life, it's decreasing by half every year, so we have the half, and we have this 5.3 here to figure out how many years it's going to have gone through, or how many half-life cycles. For instance, if this time equaled 5.3, it would have gone through 1 half-life cycle, but if it was 10.6, it would have gone through two of those. So it would have been 100 times half times half. Now it says determine the percent of radioactive substance remaining after, 10.6 years. So the first thing I'm going to do is go P of 10.6 equals 100 to the 1/2. And then I'm going to put that 10.6 here, and I'm going to divide by my 5.3. Well, this equals 100 times 1/2, 10.6 divided by 5.3 squared. And so 1/2 times 1/2, well, that 2 gets applied to the 1 and the 2, which makes it 1/4. And 1/4 of 100 is 25. So in other words, after 10.6 years or 2 cycles, only 25% will be left. The next part of this equation is asking us to algebraically determine the number of years it will take for there to be 2% of the original amount remaining. So in this case, what we're going to do, we're going to go 2% on this side, and we won't write in the percent actually, we'll leave it as 2. Here we'll write 100 to the 1/2, and here we're going to say T over that 5.3. We're going to leave that there. Now what do we want to do to solve this? Well, we have a couple of options in this case. We can try and divide both sides by 100, which leaves me 1 over 50 right here, which leaves me 1/2 t over 5.3 here. This is 50 to the negative 1. And on this side, I'm going to bring that 2 up as well, which makes 2 to the negative 1. But now I have this t to the 5.3, so that's going to be negative t to the 5.3. And if you're thinking, I would not have done this way, you're probably right. There are so many ways to do this. The next thing I'm going to do, I'm going to take the log of both sides, because that's what that's going to do. It's going to bring this out front and bring this exponent in front of the log. So I get negative log of 50. And then here I get negative t over 5.3 log of 2. Well, because they're both negative, we can get rid of that. I can divide both sides by log 2. And that's going to give me, I'm going to switch the sides, t 5.3 equals, I know I'm rewriting things. And then I multiply both sides by 5.3. And that leaves me with t equals 5.3 times log 50 over log 2. And let's go ahead and just get an approximate value for now. And go 5.3 times log of 50 divided by log of 2 gives me 29.912, and that's in years. And it says to check this graphically. Let's grab that calculator again. And here I'm going to put in my y equals, I'm going to put 2 on this side. And, oops, 2. And on this side, remember, I'm going to put my 100 bracket 0.5 or 1/2 if you wanted to, exponent x divided by 5.3. Notice I put that in brackets like that. And I'm going to need to change the window settings if I want to see any intersection here. And that's going to be at least to 30. Let's put 35. And let's graph that up. And here we go. So this one here is that exponential equation, and then this is our line of p of t equals to 2. And we're going to find that intersection, second trace, 5, yes, yes, yes. And sure enough, they also get 29.912. Well, that'll be it for the part 1 of solving exponential equations. We'll come back and look at more strategies, putting it all together. If you have any questions about any of these problems, please don't hesitate to ask. I hope you have a great rest of your day. Take care. So let's sum up some of the strategies that we've gone over so far. The first one being we have used exponents where we are writing the equation with a common base so that a to the b equals a to the c, and then we're going to rewrite the equation as b equals c and solve for the unknown. we're going to use equivalent expressions, meaning we are going, if we are given an exponential equation, we're going to rewrite it as a logarithmic equation. It's equivalent logarithmic equation. And then we're going to solve for the unknown. In this one, using logs, apply the common logarithm, in other words, base 10 to both sides of the equation. And then we can use laws of logarithms to solve for those unknowns. And the last one here is graphing, and we can always use graphing by writing an equation for each side of the given equation. Graph of these two equations, one on y1, one on y2, and then we're going to determine any points or points of intersection of the two graphs. And we can always use graphing to check any solution, or we could also use substitution. So let's use what we've learned with the different kinds of strategies to continue to solve some examples. Now this one here, a student says that you can always divide out the coefficient when solving exponential equations. And it's saying use the equations below to either support or refute his claim. So if we are going to divide out the coefficient, that 8 there, we're going to divide both sides by 8. Well, that leaves me with 3 to the 2x on this side. Looks good so far. And this one, 568 divided by 8, that is 71. Okay, so far, so good. Now, the next thing, if we wanted to go to a same base, well, that's not going to work. 71 is a prime value. So we're just going to take the log of both of these sides. So that's going to allow us to bring the 2x down to the front. And now I can divide both sides by log over 3. As well, notice here I can also take the 2. So we're going to divide both sides by 2 log 3. This cancels, this cancels, this cancels, this cancels, and x equals log 71 over 2 log 3. That seems okay. We got a nice exact value for x here. So that seemed to work in that case. Let's go ahead and see about this one here. Well, it says we want to divide out the coefficient. Well, let's do that. Well, we isolate this side, but then look what happened here. Well, we got this 1/4 here. And now we have 1/4, 2x minus 3. Not really seeing the point of this one. This one is not working as nicely as what the other one did because we can't divide anything out. And I'm kind of going, what other things could we do here? Well, I would think then maybe dividing isn't the greatest first step for this particular example because that 4 doesn't divide evenly into what's on the other side. So this tells me that we can't always depend on that dividing as a go-to first step. We have to kind of examine what we've been given and make choices based on the question. Let's keep going. So in this, it says solve the equations below using the strategies of your choice. Well, let's give this a go. The first thing here, let's see if 8 divides into 128 evenly. So we are going to try to see if it works. But if it doesn't, Oh, we got 16, so it does. It was lovely. This one is 16 to the 2x, dividing both sides by 8. It gave 16 on this side. Now, while this doesn't have an exponent, we all know that 1 is implied. We have the same base, so we can say 2x equals 1, or x equals 1 divided by 2, or if you wish, 0.5. Now we can check this by substituting it back, and let's start with the right-hand side, 2 times 0.5 as the exponent, and this is 16 to the 1, so that's 8 times 16, which is 128, and we knew the other side was 128. So the left-hand side equaled the right-hand side. Oh, look at that messy writing. And we know we got it done. Now here's one. Again, this is very similar to the other one, so we may not want to go that route where we are dividing by 4 because it really doesn't get us anywhere. So what we look at, well, do we have same bases anywhere? Well, no, that's not an option either. Can we put this into its log form? Well, no, because we have different exponents going on here with different bases. So I'm thinking the option is if we take the log of both sides. So what does that do? Well, on this side, I can take the 2x minus 3, and I can bring it down in front of the log of 8. And then I can take this log 8 and run it through here, so I have 2x log 8 minus 3 log 8 here. I can do that. What can we do here? Well, these is multiplied, so we can go ahead and make that the addition of logs. Now I can take that x and bring it out front. So I have log 4 on this side, and I can have x plus x log 7 on this side. And then I'm going to bring my x's over this way and all the other terms that way. So I have x log of 7 minus, I'm going to write it this way, x 2 log of 8 equals negative 3 log of 8 minus this log of 4 over here. Well, that leaves me on this side with x outside of log 7 minus 2 log 8, but we can put that 2 up here, and 8 squared then would be log of 64. And then on this side, I can do the same thing with the 3 if you wish. Take that 3, bring it up here, and we can say negative, and let's take the negative out, negative log 8 cubed, big number, plus log 4. And now I'm going to divide both sides by this, which is going to leave me x equals negative log 8 cubed plus log to the 4 all over the difference here, which is log of 7 minus log 64. Now I have this negative here. Well, if I ran that through the denominator, that's going to give me log of 8 cubed plus log 7, sorry, log 4. And it's going to change the signs of the bottom, so that's going to give me log 64 minus log 7 on the bottom. There we go. Now if you want to kind of reduce the number of logs even further, we can say log of 8 cubed times 4 and get that number. And then here we can get the log of 64 over 7, but I realize these are not, the 64 divided by 7 is not a nice even number. And then this 8 cubed times 4, that's a pretty big number. So either one of these is going to work. So this one is asking us to solve this algebraically and check graphically or by substitution. So let's write that out. Now another way we can start these up is, I mean, it would be nice to take this and bring it out front, but I also can rewrite this as 4 2x times 4 to the negative 1, because remember we're just going to add that, which I can rewrite as 4 2x over 4, like that, where this is 5 2x right here. And you're saying, why is this a big deal? Well, now I take the logs of both sides. I have the log of 5 of 2x equals the log of everything here in brackets. Now notice this is now the log of a quotient, which means I can go ahead and rewrite this as log of 4 to the 2x minus log of 4. Now I can take this, bring it out front, same with this 2x right here. So this is going to leave me 2x log 5 equals 2x log 4 minus log 4. Well, now I want to get everything that has x's over there, everything else over here. Well, all I can do is bring this 2x log 4 over. So this is going to give me 2x log 5 minus 2x log 4 equals negative log 4. Now notice I have a factor of 2x here. Let's take that whole thing out. Let's take that 2x out, and we're going to say log 5 minus log 4 equals negative log 4 here. And let's take that up and over, because I hate working horizontally. And I'm going to divide both sides by 2 and the log 5 minus log 4. So that's going to give me x on the left-hand side, and it's going to be negative log 4 all over 2 log 5 minus log 4. Now here, because I have this negative here, I can actually bring it to the bottom, and I'm going to run it through this binomial here, I guess this two-term thing, and that's going to change the signs. It's just a me thing. It's not super necessary. And that makes it log 4 minus log 5. And it says check graphically or by substitution. Well, let's see what we got here. So the first thing I'm going to do, I'm just going to put this into my calculator. So I said log 4, enter, divide by 2, enter, divide by log 4, make sure that 4 is in brackets, minus log 5, and I get negative 3.10628. Well, let's go and look at what our graph gives us. So first of all, we're going to put in 5. Oh, we got to put in 2x right there. So let's go 5 to the 2x, oops, 2x, like that, and then 4 to the 2x minus 1. We're going to hit graph. There's one. Oh, and there's the other. So it looks like there's going to be an intersection over here. So let's go second trace, and we're going to go 5 for intersect. Is this the first curve? Yeah, second. And let's graph her up. And we get, oh, there we go. We get that same number, negative 3.106. And if we quit out of that, negative 3.106. And we're done. Okay, so in this question is asking us to solve the equation below. Write your solutions as an exact value logarithmic expression. And which method do you prefer to check your solution? So let's go ahead and look at this here. Well, the first thing I notice, I definitely have nothing here that has the same base, and I can't divide by that 2. So the first thing I'm going to do is I'm going to take the logs of both sides. So I'm going to say log of 2 times 3 to the x minus 2 and log of 7x. The next thing, I am going to use the product of logs rule, so that I'm going to say log of 2 plus log of 3 to the x minus 2. And on this side, I'm going to take that down, so I have x to the log 7 on this side. Well, this whole thing here, I'm going to bring down into the front, and that gives me log 2 plus x minus 2 log of 3 equals x log 7. So now here I have this has to be distributed through this whole thing. So I'm going to get x log 3 minus 2 log 3 right here, and I still have this log 2 right here. Now I'm going to get all my x's to one side and everything else to the other. So this means on this side, I'm going to have x log 3 minus x log 7. And then this term and this term have to come over to the other side. Therefore, the signs get flipped. So this is x log 3 minus log 7. And that's going to equal, well, here, let's do something first. Let's put that 2 on the 3. That becomes 3 squared. And that's going to be 9. So log 9 minus log 2. And here I'm going to divide everything by log 3 minus log 7. So that's going to give me x on this side, then log 9 minus log 2 over log 3 minus log 7. Now it's asking us to check the solution and which would we prefer. Well, because we have this exact value here, substituting this big expression back into the original equation kind of looks like it's going to be a lot of work. I might want to say, well, what is the approximate solution of that? And I would grab my calculator and I would go ahead and I would say log 9 minus log 2 divided by, now here I'm going to go log 3, close the bracket, minus log 7, close the bracket. And that's going to get me negative 1.775 approximately. At this point, I'm going to go back into my calculator and I'm going to put in the left and right hand side of this equation. So I'm going to say 2 times 3 to the x minus 2 in brackets. And then on the right hand side, I'm going to have that 7x, oops, one more, 7x right here. Then I'm going to hit graph. Going to wait some more. So we can see there's probably this intersection going on down over here. So I'm just going to use this. And sure enough, I get negative 1.775. Now, so in some cases, it may be just a matter of time and quickly determining whether a solution works by graphing might be the better option. If it's a quick, easy substitution, however, I probably would go with that. So again, this is my exact value, and yeah, it works. If you have any questions about anything you've seen in today's video, please do not hesitate to get in touch. Have a wonderful rest of your day.